but of course what we're really interested in is representing real systems. And here we've had a sustained effort with all these people involved over the last 5 or 6 years, and it's very important that we're coupling the experimental and modeling approaches. So the first thing we had to come to grips was that, you know, cement has a very wide range of particle sizes. It had particles up to 50 microns, going down to well below 1 micron. And unless you deal with this, you find that, you know, you really can't see anything because everything merges into the same kind of curve. So we had to start synthesizing these minerals. We find that if we synthesize pure C3S, we get something like this, which is not at all like the cement that we want to represent. So we have to go to other systems. We have to separate out the particle sizes, and then experimentally we can look at their hydration kinetics by looking at the heat evolved with isothermal calorimetry or chemical shrinkage and a variety of other techniques. And then we find, after quite a lot of hard work, we can represent the basic mechanisms, and basically at the early stages it comes down to two things. It comes down to dissolution, nucleation and growth. These are phenomena that are quite well known in other fields. We can do this with a very fine level of resolution. What we can do, we put in the particle size distribution, the composition, the water, cement, etc. We can represent how the different concentrations in solution evolve on a scale of 0.1 seconds. We can calculate what phases can be precipitating, and we can use the models from other fields. So this is studies we made from the field of geochemistry, where people have found that as the concentration of the solution changes, the pattern of dissolution changes. And we did studies which showed that this could be quite relevant to the reaction of cement. So just to take a bit longer to explain this, what this slide actually shows, this shows us that if we take freshly manufactured alite, which is the main phase in cement, and we dip it in pure water, we can see very quickly we get the formation of these edge pits all over the surface. So in pure water, the dissolution is very fast, the reaction rate is very fast. On the other hand, once the solution becomes saturated with calcium, if we have a saturated lime solution, this is already enough to drastically slow down this reaction so we don't get this formation of edge pits. And by understanding this process, we can then represent it mathematically, we can fit the parameters according to the experimental detail, and we can really capture what is happening in our materials. Once the reaction is renewed again at the end of the so-called induction periods, we switch to a different mechanism. This is another classic mechanism in science of nucleation and growth. And again, here we find some interesting phenomena. For example, if we try to simulate the growth of CSH on the alite particles in a classical manner, we find that, unfortunately, it does not fit with the experimental results. So by having this model which enables us to quantify these effects and to look at them over the range of particle sizes, we come to the point where we put into question what are quite accepted mechanisms of hydration. Many textbooks say that what happens here is you get diffusion kicking in, but also we can go through a process to show that this is not true because this is a large particle, this is small particle. What we see here is that at that maximum peak, the thickness here is quite different from the thickness there. So this, again, contradicts the well-known theories of hydration. And in fact, it led us to a new proposal that, in fact, these hydrates are not growing in a uniform manner. What you see here in these micrographs, this is the hydration product forming around this cement particle, and you see the density of hydrates, the packing of hydrates here is much higher than out here. So it's not a uniform growth, it's something that grows out very fast in a very diffuse manner and then subsequently densifies. And when we capture this kind of reaction mathematically, we can then get very nice fits across the range of particle sizes. So we can put all that together. Here you see the fitting across the range of particle sizes. We can bring in the study of the illuminate phase, as you see here, and then we can simulate these microstructures really of very, very complicated systems. We can vary different things, such as the size of the particles, such as the levels of sulfate addition. We can now well capture the kinetics of even commercial cements, as shown here. And we can look at things like the effect of inorganic salts. You see here we well capture the evolution of the solution concentrations as seen in the literature. We can see what happens with different mixing speeds. Here you see that with different speeds of mixing, you have a considerable acceleration of the hydration. This is reflected in the change of the parameters in the microstructural model, and is also reflected in what we see in the rear microstructures, that if with a very fast mixing speed here, you have a much denser and homogeneous microstructure than this microstructure over here. So we now have a model that really can well capture hydration kinetics of even quite complex systems and can give us the microstructure. So of course the next challenge is the second step of the problem: how do we extract the properties from this microstructure? And here we're still at the beginning of the process, because here we meet a whole new range of challenges. Just to give you some small insights in this, the first very simple question, or seemingly simple question, is, how do we understand the pores? We talk all the time about pores in cement and concrete, how important they are for strength and durability. But you see the pore structure, which is the black part here, is a very complicated entity. And it's, again, a computational problem. How do we manage to extract these pores down to very small sizes? With our latest advances, we can now get those pores, we can now model those pores down to a 5 nanometer size, which is starting to be the level that we need to get to really understand the properties. And of course, we can show that conventional methods for measuring pore size, like mercury intrusion porosimetry, because they're actually looking at pore opening, do not well capture the pore size. We, of course, want to go on and look at mechanical properties, and particularly we're interested in how these properties develop during the hydration process. It's comparatively easy to capture the effect on final properties, but from a practical point of view, we want to know how fast strength develops when we can demold the concrete, etc. And here we bring in different mathematical methods. This is finite element modeling, which of course is now generally used on a structural scale. The challenge becomes, can we use this on a microstructural scale, which instead of having nice symmetric structures, we've got really very complicated microstructures to mesh. So this is a challenge. It's a challenge because when we've got voids and when we put those into a mesh, we tend to connect things together again, which can give us really completely the wrong results. But nevertheless, despite all of that, we are making progress, and we can see things, for example, that the level of flocculation, the level of agglomeration in the cement paste, which of course is affected by things like superplasticizers, can have a very important impact of when you start to see the strength developing. This is the set point, etc. And overall, when we compare the results to the experimental measurements, we see that really it's not too bad. It's not too bad, but we've still got quite a long way to go before this can really give us the performance that we'd like. Swapping scales, because we're not just working at cement paste level, we're also working on durability problems. Here are some small slides from the issue of alkali-silica reaction. And again, what we're trying to do here is relate what's happening in the microstructure to what's happening macroscopically. And we can do this by really understanding what the microstructural processes is. In a lot of aggregates, particularly aggregates we really find in effective structures which react very slowly, we find that the alkali-silica reaction happens within the aggregates. We can quantify that by this image analysis technique, and what we can in fact see is that the amount of reaction correlates very, very well with the macroscopic expansion across a whole range of different aggregates. And we can use this observation then to put together a model where these are the aggregates, these are the gel pockets inside it, and this can then give us very good agreement with experimental results. And ultimately, we hope this kind of model can enable us to bridge the gap between accelerated laboratory tests and behaviors of real structures. So just to finish, to really try to summarize what I've tried to give you some insight into, I think modeling of cementitious materials is really an essential tool to the development of more sustainable concrete. We need to build these models up from systematic science-based understanding of processes that occur at micro and nano scale, and then extend across these different scales to eventually provide the multidisciplinary assessment and predictions tools we need to ensure the good performance of current and new material. So there's many challenges there, but I think these can be overcome on fairly short timescales if we have a coordinated approach linking experimental, mental and modeling studies. So finally, I'd like to acknowledge all the people who contributed to this work, who are very numerous, all the entities that funded our work, and thank you very much for listening.